Hi, I want to tell you about my new method for generating complicated shapes. I've been working on this for many years, and it was just accepted into the top computer graphics conference, SIGGRAPH. Imagine you're making a video game or a movie. To make it feel realistic, you need to add lots of shapes and geometry. This can be very difficult and expensive, but I'll tell you how you can automate this. My method uses something called a graph grammar. Let me explain this. A graph is a set of vertices connected by edges. A graph grammar is a set of rules that modify a graph. Now you may wonder, why is it called a grammar? This is for historical reasons. This has little to do with language. For example, here's a graph grammar with 5 rules. One rule creates a rectangle. Another rule takes a straight line and adds 2 corners to it. By applying different rules, we can create a variety of different shapes. Graph grammars are really powerful because they can create so much variety and complexity with just a few simple rules. And the exciting thing about my new method is that I can generate the rules of the grammar automatically. Grammars themselves are not new. People have been using grammars to generate shapes for decades. But most past work assumes that you have an expert who can design the grammar for you. My method works automatically. Here's the idea. You provide an example of the type of shape you want, and my method will automatically create a grammar from the example. The grammar will generate shapes that are similar to the example. What does it mean to be similar to the example? If you look at any small part of the new shape, it must match part of the example. Each one of the new vertices must match a vertex in the example. This is called local similarity. On a small local scale, these two shapes are the same. But on a large scale, they can be very different. How does this compare with other work in the field? There are many methods that create shapes using a slightly different kind of grammar. They can produce very impressive results, but they're not automatic. An expert has designed the grammar, and this is hard to do. Creating a grammar that will produce a particular set of shapes is not straightforward at all. Today, this process looks more like computer programming than artistic design. There are some methods that do create grammars automatically, but they're limited to particular types of shapes, like building facades or trees, which are relatively easy to handle. I worked on something very similar for my PhD. I created a method that could generate locally similar shapes based on an example, but the shapes had to fit very neatly onto a grid. I called my method model synthesis. My approach caught on with game developers, and it's been used in games like Townscaper and Bad North. Many people have heard of this method under a different name. My work on model synthesis inspired Maxim Gumin to create a similar method he called wave function collapse. Maxim popularized my academic research. He put it into the hands of a lot of game developers. But it's not a different algorithm. It's very similar to model synthesis. The main issue with this kind of approach is that the shapes must fit very neatly onto a grid. In several of my papers, I developed strategies to work around this, but this is still a major issue. We've talked about past work, now let's talk about my new method. My method generates graphs. It generates edges and vertices. Initially, the vertices won't have a position. So when you see a graph like this, you should imagine that the vertices can move and the edges can stretch. We will add positions at the very end. Here's an overview of my method. We start with an input shape. We cut this shape into small pieces called primitives. We glue the primitives together in as many ways as possible using every possible combination. This gives us a set of possible graphs, and we organize them into a hierarchy. We use the hierarchy to create a graph grammar. Ideally, this grammar can generate every locally similar graph. At the very end, we assign positions to the vertices and add decorations if needed. My method begins with an input shape. The faces of the shape can be filled in with different colors. Each edge is labeled based on local similarity. 2 edges have the same label if they have the same angle and the same colors on the left and on the right. Every edge can be cut in half. It can be split into 2 half edges. And we can reverse this. We can glue the half edges back together to make a full edge. We can glue many half edges together to construct a large graph. A graph is complete if it has no remaining half edges, and so it can't be glued to anything. We can also glue half edges together to form a closed loop. A closed loop must turn 360 degrees. If the path turns more than that, the path will intersect itself. So we need to calculate how the angle changes along the path. Consider this circular path. The angle starts at negative 180 degrees. It continues to increase as we go around the circle until we reach the angle plus 180 degrees. Plus 180 and negative 180 are really the same angle. We keep track of how many times the angle crosses this threshold at 180 degrees. If the angle goes from positive to negative, we call it a positive turn. It looks like a hump. If the angle goes from negative to positive, we call it a negative turn. It looks like a dip. The positive and negative turns cancel each other out. If after canceling, we're left with one positive turn, that means that the path has turned 360 degrees. Now, I can precisely describe which half edges can be glued together using something I call the graph boundary. To find the boundary, we trace a path around the graph and we write down every half edge and every turn we find along the path. There's now a simple formula for determining if two half edges can be glued into a loop. There's a formula for gluing the boundaries together. The boundary fully describes how the graphs connect together. If two graphs have the same boundary, one graph can seamlessly replace the other. This will become important when we talk about graph grammars, since grammars are about replacing graphs. Now that I've explained some of the terminology, let's get back to my method. We begin with an input shape. We cut every edge in the input into two half edges. We're left with a set of basic building blocks that I call primitives. We glue the primitives together to form larger graphs. We consider every possible way that we can glue these primitives together, and we save the results in a graph hierarchy. This hierarchy starts at generation 0, or just gen 0, and it starts with the simplest graphs, the edges. We attach primitives to the gen 0 graphs to get the gen 1 graphs. We attach primitives to gen 1 graphs to get the gen 2 graphs, and so on and so forth. In addition to attaching primitives, we can also glue loops together. The next step is the hardest part. We're going to use the graph hierarchy to create a graph grammar. First, let me give you some background on graph grammars. There are several different approaches to graph grammars. We're going to use the gluing approach, also known as the algebraic approach. Within that approach, we're going to use double push-out graph grammars. The term push-out comes from a branch of mathematics called category theory. Now, you don't really need to know category theory to understand this, but that's where the term comes from. A double push-out graph grammar consists of production rules. Each rule has a left side, a right side, and an interface between them. To apply a rule to a particular graph, we match part of the graph to the left side of the rule. We remove that part of the graph, and we replace it with the right side of the rule. In my method, the left and right side of each rule will consist of two graphs with the same boundary. They have the same half edges and turns. This means that one graph can seamlessly replace the other graph, and this preserves any 360-degree loops. We can create a rule if we can find a left graph and a right graph with the same boundary. But we can also combine multiple graphs together. Here we have two graphs on the right. We can combine their graph boundaries so that the combination matches the left graph boundary. Here's an overview of my approach for creating the graph grammar. Like we did before, we start with the primitives and we build a graph hierarchy. We add graphs to the hierarchy one by one. Each time we add a graph, we check if it's possible to create a rule that will simplify the graph. If it is possible, we remove the graph and all of its descendants from the hierarchy. If a graph can be simplified, if it can be reduced to a simpler form, we say that the graph is reducible. Ideally, we would continue adding rules to the grammar until every complete graph is reducible. What do I mean when I say that one graph is simpler than another? There are many ways we could define simplicity or complexity, but for our purposes, a graph is simpler than another graph if it has fewer half edges. If they have the same number of half edges, a graph is simpler if it was added to the hierarchy first, before the other graph. I claim that if a graph grammar can simplify every complete graph, then it can construct every complete graph. Let me show you why. Imagine we start with any graph. The grammar can reduce it to a simpler graph. The grammar can then reduce that simpler graph to an even more simple graph. The grammar can continue to make the graph simpler and simpler until we reach the simplest possible graph, a graph with nothing in it. This grammar can reduce any complete graph to nothing, and each of these steps can be reversed. If a grammar can reduce any complete graph to nothing, it can reverse this. It can construct any complete graph from nothing. Let me show you some examples where we start with a complicated graph and reduce it to nothing using just a few rules. Here are shapes that are locally similar to a diagonal box. First, we apply a rule that takes a diagonal graph and deconstructs it into two parts. We apply additional rules to simplify the graph. We're left with some diagonal boxes that can be removed by a rule. I've now given you a quick overview of my method of creating grammars, but there's still a couple parts of this that I need to explain more. First, how do we find the rules to reduce the graphs? Second, there's another more complicated way of reducing graphs that I'll need to explain. And third, there are often some graphs left in the hierarchy that cannot be reduced and cannot be completed. How do we find a rule to reduce a graph? Remember, to create a rule, we need to find another graph with the same graph boundary. It's not difficult to go through every graph in the hierarchy and just check if their boundaries match. But we can do something more sophisticated. We can match one graph on the left to multiple graphs on the right. And now I'll explain how to do this. Assume we have a graph we want to match on the left. The hierarchy contains a long list of possible graphs we could use on the right. We attempt to match each of these graphs to the left graph. If we find a partial match, if we can match some of the half edges, then we just need to match the remaining half edges for the two boundaries to fully match. This is a recursive algorithm. For the remaining half edges, we follow the exact same procedure for finding a match, and we continue until every half edge is matched. Each time we add a graph to the hierarchy, we check if another graph can reduce this graph. But we can go the opposite way. We could have the new graph reduce an existing graph. Now there's something slightly complicated that can happen. If you're not careful, you could reduce a graph to itself, which is not good. I talk more about this in my paper, and I plan to make another video about this. There's one type of graph that's very useful if you can find it. If you can find a graph with one half edge, this is extremely useful for reducing other graphs, and sometimes this by itself can solve the whole problem. There's another issue we need to discuss. Here we built a hierarchy, and we found rules that can reduce most of the graphs in the hierarchy, but not all of them. There are still some graphs that cannot be reduced. Some graphs can continue spiraling in circles forever, but none of these graphs are complete. We can prove this. We can prove that every graph in this hierarchy is either reducible or incomplete. This is a complicated issue. I'll discuss this more in another video and in my paper. In this example, and many others, we can prove that every graph is reducible or incomplete. But we don't always come to this happy conclusion. In some cases, the hierarchy grows very, very fast. There's just so many possibilities to consider, and it's very difficult computationally to consider all of them. This is an important topic for future work. Okay, we've gotten through the hard part. We began with an input graph, we cut it into primitives, we built a graph hierarchy, and then a graph grammar. The final part is to use the grammar to make new shapes. We will start with an empty graph and randomly apply rules from the grammar to make new shapes. This is an iterative process. We make many small changes to an existing shape. At each step, we apply a rule. We do this by matching part of the shape to one side of a rule. Then we replace that side of the rule with the opposite side. Remember, I said that we weren't going to add vertex positions until the very end. We've now reached the end. Suppose we have two vertices connected by an edge. We don't know their position, but we do know the direction of the edge. From this, we can write down an equation describing the vertex positions, the edge direction, and the edge length. We get that equation from one edge. We can write down similar equations for the other edges. Then we solve these equations. There are often multiple possible solutions, and we randomly pick one of them. Sometimes the solution we picked is no good. It might cause the edges to intersect. After we pick a solution, we check that it satisfies several criteria. If it does, we accept it. If it doesn't, we pick another solution until we find a good one. To summarize, we generate shapes by randomly applying a series of rules. At each step, we apply a rule, we sample from a set of solutions, and then we accept or reject the solution. Additionally, we can bend the edges to create curved shapes, and we can add decorations to the faces, vertices, and edges. So far, we've only looked at two-dimensional examples, but this idea can be extended to 3D shapes. In 3 dimensions, we start with a 3D shape, we cut it into primitives, we glue the primitives to create a graph hierarchy, and then we match 3-dimensional graph boundaries to find the graph grammar, and then use the grammar to generate 3D shapes. The process is really quite similar for 2D and 3D shapes. The main difference is that there are just a lot more ways that you can glue 3D shapes together, and that can be hard to deal with. I've created a program where you can sketch out a shape and then generate more shapes like it. Notice here that I'm bending the edges so they're not perfectly straight. My method can generate castles. It can generate flower patterns. It can generate islands with rivers on them. It can generate a space station. It can generate a factory with ladders and pipes. It can generate a residential neighborhood with streets, houses, and trees. It can generate a village with houses on top of hills. It can generate trees. Now let's look at 3D shapes. From an example shape, my method can generate similar shapes, in this case, a city skyline. My method can generate houses. It can generate a town on the water with a boardwalk path between the buildings. And finally, it can generate a futuristic sci-fi city. How does this compare with other methods? Many other methods use grammars to generate shapes. Often they use something called a shape grammar. Shape grammars work by splitting shapes into smaller components, but graph grammars are much more flexible. And most other techniques use rules designed by experts, while my method generates the rules automatically. There are some other methods that generate rules from an example, but they only work on some shapes. They usually can handle trees pretty well, but they have trouble with loops. Trees are easy to generate. Any shape that branches out like a tree can be completed pretty easily, because the branches can all have dead ends. But shapes with loops are much harder. Dead ends are not allowed. We must find a way to form each and every path into a closed loop. If we try to grow it out like a tree, it often becomes difficult or impossible to complete the shape. There are only a few methods that even try to solve this problem for general shapes. They typically fail in one of two ways. Either the loops are broken, or the output is just a copy of the input with no new variations. The most similar method to mine is the very influential work of Bachlo et al. Their method also takes an input, cuts it into pieces, and then glues the pieces together. But they only allow the input to be cut at certain places they call docking sites. This is much more restrictive than my primitives. Again, this causes problems when the input shape has loops, and this means that their method only produces minor variations on many input shapes. My method has many limitations and many ways it can be improved. I'll just mention two of them. First, you don't have a lot of control over the results. The shapes it generates are pretty random, and this can be improved. Second, for some input shapes, the graph hierarchy grows so rapidly that it's very difficult to deal with. In this case, I can't guarantee that my grammars can produce every locally similar shape. I've covered a lot of material. I want to leave you with two main takeaways from the video. First, graph grammars are a very useful tool for generating shapes. Second, I really like this idea of organizing all possible shapes into a hierarchy and then analyzing them that way. I think it's very powerful. I've just been talking about locally similar shapes, but I believe this can be extended beyond that to many other interesting problems. For more info, go to my website, paulmerrell.org. On my site, I have a demo you can try out. It has about 80 different shapes you can use, and I'll be making more videos, so please click subscribe.